So the next topic we're going to talk about is called equilibrium. Now I've pulled this picture. If you watched the previous videos, this is one of the concept questions that was asked. I pulled this picture just to talk about equilibrium with. By equilibrium, there's two types. There's static equilibrium, meaning the object stays stationary. I guess we could say the system, because this is not a single object we're looking at. So the system is staying stationary, at rest. It's not moving. We don't want it to move. It's not going to move unless something fails, like the bolt on the left end. Dynamic equilibrium is an object that is moving but has no acceleration. And by that we mean no tangential acceleration. So it's not speeding up or slowing down in any way. So no tangential acceleration, no linear acceleration, no angular acceleration. So it's rotating at a constant rate. We're going to focus on static equilibrium, though we could certainly, it's not terribly difficult to extend that to dynamic equilibrium. In either case, to not have any acceleration at all, we have to say that the net force is zero and the net torque is zero. So both of them need to add up to be zero. In this section on forces, we looked at problems where the net force was zero, but we were focusing and pretending the objects were all essentially particles, so we weren't needing to account for any rotation. Here, though, this massless rod, it's holding the 1,000 Newton mass at the right end. There's a scale in the middle, a pin at the left end. Excuse me. Well, if this mass disappeared, or the pin broke, or the scale crumpled, there's different results in what would happen. And so there's different rotations ultimately. So the rod as a whole is not going to behave exactly the same way a small little golf ball would, for example, if we let go of it. And so we need to account not only for the net force being zero, but also the net torque being zero. Now this problem, when you saw it before, it asked you for the reading on the scale. I want to approach this, though, the way I would approach an equilibrium problem. Similar to when we were covering forces, we do need to draw a free body diagram. And we need to draw the free body diagram for whatever object connects everything together. In this particular case, I would be drawing the free body diagram for the rod. The rod itself is what is holding on to the 1,000 Newton mass. It's the one that is feeling the force from the scale. It is the one that has a pin at the left end. So I would draw the rod, and we have to be very specific about where we draw the forces. Because torque, remember, depends upon how far that force is applied from the lever arm. So we have to be very intentional and careful about where we're drawing the forces. So I would draw the force of the 1,000 Newton mass hung at the right end. I would draw that at the right end. The scale is pushing upwards on the rod in the middle. So I need to draw that force in the middle. The pin down here is exerting a force as well. Now, if we're not sure about which direction the forces are in, if it has X and Y components or not, we can choose those X and Y components however we want. And the math, as long as we're accounting for them correctly, the math will work out and tell us if we were right or wrong. So for example, let's say I wasn't sure. So I said, well, maybe the pin pushes inwards this way. I'll call that I'll just call it Fx. And then maybe I thought the pin might be pushing upwards. And you might be saying you're so wrong, which I am, but I'm being wrong intentionally. Because for some, it may not be obvious, and that is okay. So setting up our equations. For example, in this quiz question, we were asked to find the force that the scale was applying. Now, we have to say that the net force in the X direction has to be 0. The net force in the Y direction has to be 0. Technically, the net force in the Z direction needs to be 0 as well, but we're not working three-dimensionally here. We know the net torque around any axis must be 0. From experience, I have learned that some problems can be solved using and writing out the net torque equation. So let's start with that one. The net torque on this rod as a whole must be 0. Now we can put our rotation axis wherever we want. I highly recommend choosing the rotation axis to be at a location where you have an unknown force or you have your most unknown forces. So when I'm going to set up my torque equation, I'm going to write that equation based off of the left end where that pin is located. I'm going to represent that as my rotation axis. And the reason why, if we remember, torque is R, the lever arm, times the perpendicular component of the force. Well, if my rotation axis is at the left end, R is 0 for both the Fx and Fy. So neither of those are producing torques. So they will not be in the equation representing the net torque, which is nice. So my equation over on the left, the right, I will write it. I will need to add up the torque caused by the scale's force plus the torque caused by that 1,000 Newton hanging mass. Those need to add up to be 0. Otherwise, there would be a net torque, and that would cause rotation. So this is our fundamental equation representing the net torque is 0. Now, the torque caused by this scale. I would draw my lever arm from the rotation axis out to this force. So this R for this scale, I'm just going to write it as half the length of the entire rod. So the entire rod is a length L. So R is 1/2 L. The force is, I'm just calling it force of the scale. Now, those are already perpendicular, right? The angle between these is 90 degrees, so I'm good. If we were using the RF sine phi equation, phi would be 90, so that just gives me 1. Now, if that force was the force causing rotation, if there was not 1,000 newtons at the other end, this would tend to rotate, this would cause that rod to rotate counterclockwise. Counterclockwise is the positive z direction, so we would say this is a positive torque. The 1,000 newtons would cause clockwise rotation, so it's going to be a negative torque. The lever arm starts at the rotation axis and goes all the way out to the end. So this is the entire length of this rod. So R is L, the force is 1,000 newtons. These are already perpendicular to each other, so sine of 90 is 1. So these numbers are what are going in for my torques in the net torque needing to be 0. If you wanted to, you could totally jump to the magnitude of these torques needing to be equal to each other to balance out the rod. So when we get to that point, we see that the force the scale must apply to maintain this rod in equilibrium is 2,000 newtons. Now, recognizing that the scale was closer by half means the force has to be double, so you don't necessarily need to go through the whole setup. Unless, of course, you're not sure, then this setting up the net torque being 0 can help us calculate for it. Now, I want to take one step further and come back to these forces and talk about these. The net force in the x direction needs to be 0. The net force in the y direction needs to be 0. So if I was writing out my equations, coming back to my picture, remember I drew an x component of force. If I didn't happen to know if there was one or not, I drew one in. But there is no other x component of force. So mathematically, I can also show myself that there needs to be no force in the x direction. This x component force from the pin in this specific case needs to be 0. Otherwise, if there was an x component of force, it would cause horizontal motion. In the y direction, for the pin, I'm going to just draw a separate equation. So the pin, I drew it having a y component of force upwards. I already know the scale's force is upwards. And I know the 1,000 newtons hanging at the right end is downwards. So this here represents my net force in the y direction, and it must equal 0 to be in equilibrium. So we find that Fy is the 1,000 minus the force of the scale, which we've already calculated needs to be 2,000. So we find that Fy is negative 1,000. What that means, coming back to my picture, is I drew it in the wrong direction. The pin pulls down. So I was just wrong in my direction with a force of 1,000 newtons. Now, part of the reason I walk through this is because I know many students take statics, and you will have a lot of problems where you may not know what direction the y component or x component forces from pins or whatever are. You might not know the direction of the force. And this is the approach you would take. You just go ahead and choose a direction, you draw it in your free body diagram, you set up all your equations based off the direction you've chosen. Your algebra, the mathematics of it, will let you know if the direction was right or not. If we came up with a positive answer, the direction we drew would have been correct. All right, so I'm gonna do a couple of example videos as well. So equilibrium, we mean net force on the system in general is 0, the net torque is 0, but we need to choose and isolate one object that ties everything together to draw the free body diagram and write out the net force and net torque equations.